AP Style Free Response Problem 3. These data were determined from experiments with this reaction. 2NO plus 2H2 produces N2 plus 2H2O. We have a set of 5 experiments with concentration values and rate values. A, determine the order of each of the reactants, NO and H2O, from the data given and show your reasoning. B, write the overall rate law for the reaction. And C, calculate the value of the rate constant K for the reaction and include units. D, for 2, calculate concentration of NO when half of the original amount of H2 has been consumed. For 5, experiment 5, fill in the concentration of H2. Part F, these elementary steps were proposed for the mechanism of this reaction. Based on the data, which is the rate determining step? We have 3 steps there. Show that the mechanism is consistent with part 1, the observed rate law for the reaction, and 2, the overall stoichiometry of the reaction. All right, let's first determine the order of each of the reactants, NO and H2, from the data given. So we're going to start with experiments 1 and 2, where we're holding the concentration of the NO constant. So what's happening to the concentration of the H2 from experiment 1 to experiment 2? We are doubling it, multiplying it by 2. What is happening to the rate as we go from experiment 1 to experiment 2? We are also doubling it. So if I double a reactant and the rate also doubles, that's a first order relationship. Comparing numbers 1 and 2, the reaction is first order with respect to H2. Now let's compare experiments 3 and 4. So we're holding the H2 concentration constant so that we can look just at the NO concentration. So what is happening as we go from experiment 3 to experiment 4? This is times 2. Now 0.3 to 1.2 would be times 4. So I doubled the reactant concentration and increased the rate 4 times. So 2 to what power is equal to 4? The order here then, oh, that's not right. The order here then is 2, second order. So comparing numbers 3, experiments 3 and 4, the reaction is second order with respect to NO concentration. All right, so that's part A. Part B says, okay, now write the overall rate law for the reaction. So now that I know the order with respect to each reactant, I can write my rate law. The rate law is R rate equals K, rate constant, times concentration of NO squared, because it's second order with respect to NO, times concentration of H2 to the first power, since it's first order with respect to H2. Now you don't have to write these ones here. I'm just putting it here for emphasis so that we can see that the reaction is overall third order because the sum of these exponents, 2 plus 1, is 3. Calculate the value of the rate constant K for the reaction and include units. So in order to do this, we just substitute the data from any of the experiments into the rate law to solve for K. In this case, we use the data from experiment 1. So rate is equal to K times concentration of NO squared times concentration of H2. So K is equal to the rate, which is 1.8 times 10 to the minus 4 molarity per second, over 0.0060 molar is the concentration of the NO. We need to square that, times the concentration of the H2, which is 0.0010 molar. So we get 5.0 times 10 to the third molarity to the minus 2 seconds to the minus 1 for our rate constant K. For experiment 2, this is part D, Calculate the concentration of NO when half of the original amount of H2 has been consumed. So first of all, the original amount of H2 is 0.0020. So half of it would mean that 0.0010 moles per liter of H2 has reacted. Okay, and also of note, for every 2 moles of NO that react, 2 moles of H2 also react. So that's a 1-to-1 ratio. Okay. Now, once we know that, the amount of NO that reacts will also then be 0.001 molar. And here is a little bit of stoichiometry I can write to show you that. So 0.0010 is half of the original concentration. It's moles per liter. If we multiply that by 2 moles of NO react with every 2 moles of H2, then this unit cancels, and we get 0.0010 moles of NO per liter. Okay, so now that's how much reacts. That's how much NO reacts. That's not what we're asked though. We're asked calculate the NO when half has been consumed. So in other words, how much is left? So the remaining NO is the starting amount, 0.0060 minus 0.0010, the amount that reacted, for a final amount of 0.005 molar. Okay, part E. For experiment 5, right here we have this question mark for the H2 concentration. So we're just going to use the rate law. And we've already calculated K in a previous part. So we can find the concentration of the H2. So here's our rate law. The concentration of H2, if I rearrange, is the rate over K times the concentration of NO squared. So let's just substitute. So some of this is experimental data, right? The rate is experimental. The concentration of NO is experimental. But this value of K is the one we found back a couple parts back. So we're just using that answer here. Okay, so we can just plug our values in and solve, and we get the concentration of H2 is equal to 2.8 times 10 to the minus 4 molar. All right, so part F is the longest part of the problem. The elementary steps proposed for the mechanism are shown here based on the data, which is the rate determining step. So I wrote rate laws here for reference for each elementary step, where K1 is the concentration of NO squared. K2 is concentration of N2O times concentration of H2. And K3, rate for the third one is K3 times concentration of N2O times concentration of H2. So, show that the mechanism is consistent with the observed rate law for the reaction. So here's the observed, experimentally determined rate law. And if we're going to propose a series of steps, we have to make sure that those steps or that mechanism is valid. Step 1 cannot be the rate determining step since it does not include H2, right? So this is not rate determining. That means it's either step 2 or step 3. An intermediate in step 2 or 3 would have to be substituted for through the use of a reversible reaction. Step 1 has a reversible reaction and would allow N2O2 to be replaced by NO, which would make step 2 the rate determining step. Let's check it out. So, for the reversible reaction, I set the rate of the forward reaction equal to the rate of the reverse reaction. The rate of the forward reaction I've already written up here, K1 times concentration of NO squared, which equals the inverse of that, K minus 1, times the concentration of N2O2 for the reverse reaction. Remember, I'm trying to substitute for this intermediate step right here. Intermediate species. So I solve for that, and I have this ratio of the K values. Okay, so I'm going to take this whole thing and substitute it in place of N2O2 here. Okay, so what I end up with is a ratio of K values, which we can rewrite as just the overall K for the reaction, times the concentration of NO squared times the concentration of H2. And that yields the experimental reaction rate. So step 2 is the rate determining step. This is the one that we would call the slow step. The last thing we need to do in part F is show that the mechanism is consistent with the overall stoichiometry of the reaction. So we already showed that it was consistent with the experimentally determined rate law, and we determined that step 2 is the rate determining step. Now we need to just show that it's consistent with the overall stoichiometry. So for a multi-step mechanism to be viable, adding its steps must result in the overall reaction. And so I've taken each of the proposed steps and added them together, eliminating any intermediates, and in the end I get the same overall reaction that I'm given in the problem.